All right, welcome back to Lag Programming, and this is compiler design. And right now we're just working on a basic command line interpreter. Really, it's interpreting what we type in. Right at the moment, it's capable of understanding a couple different kinds of expressions and doing the actual math. There's a couple of things I want to explain about this. This is handling literals. So the compiler itself, because these are numerical literals within the code, can actually do the math. It doesn't have to emit something that does the math later. It can do it during the compilation process because we're dealing with literals. At some point here, we're going to start dealing with variables, or what we call L values in the compiler world. And these L values are places where you can assign information to those L vals, and they can change at runtime, which means that we have to be able to handle those in some way. All right. So what we're going to start with is start talking about what an abstract syntax tree is. And so I'm going to start by adding a new file right here that I'm going to call ast.h. And I'm going to do my usual thing here, which is if ndf underscore ast underscore h define and if. All right. So what we want to do is create some classes that can connect together to start forming up what the language is. And at the moment, we only have a couple of things to deal with, and that's float literals and integer literals. But we're going to expand upon those. But this will set up kind of the basis of how that works and what we're going to put out. It'll also give us something that we can return to our main application, so it can work on whatever command that has been processed by this is executed in some way. So I'm going to create a class called node, and it's going to be the base class of our abstract syntax tree, and it's going to have a couple of pure virtual methods. One of those is going to be, we need to add some includes here. We're going to do IOStream and string. So we're going to return a standard string, and we're going to call this method toString equals 0. And that'll allow us to easily print out information about each node, and each node in the system can decide how it wants to be displayed by returning a string that represents its internal contents. And that just makes it very easy. We can rip through each of these and just print out the result of toString from each of the nodes. All right, so now we're going to have another class. We're going to call it float literal, and it's going to be publicly inherit from node. And it's going to have a protected value in case we want to derive from it in some way. In this case, it'll be a double, a double, and we'll just call it underscore value. Private, this needs to be public then, and we need a constructor. So this will be float literal, and it will take a double called value, and we will simply initialize underscore value to that value. There we go. And I want to have I'm going to create another base class in here. Oh, class. No, that won't work. Actually, this would be an opportunity perhaps to do a template. Then we wouldn't have to create. Yeah, let's do that. Let's create a template. Excuse me, template. Type name T. We'll make this a template class. Instead of calling it float literal, we'll call it literal. It will have a T value. It will be literal. It will be a T. Oh, I spelled that wrong anyway. A T value. And we'll update the value with value. We will. This might make doing the toString a little complicated. We could use traits to limit to specific types, but what we want to do now is T get value and return underscore value. And you know what? I'm going to take this toString out. We'll do that differently. I'm just going to have this class called node. That's just to be able to containerize them. And so here's our ones. Now we could create specializations of this right here, but yeah, I don't really need to. We have a node now called literal that can be either a float literal, an int literal, a string literal, a boolean literal, or whatever it may be, and it's based on node, so it can be cast to a node through its pointer. And that's all we need at the moment for an abstract syntax tree. It's very simple, but what we will do is come over here to parse.y, and here in this code section up here, I'm going to create. I want to include. We'll include vector. Just to give you an idea of how we can create nodes. We'll get into more sophisticated nodes that have child nodes and so forth later once we start putting together some different kinds of structures. Now remember, I said that the compiler is interpreting these expressions. So we don't have like a tree of this expression that does the calculation. We're just going to store the final value of whatever expression it is and put it in this vector that I'm going to create, and it's going to be standard vector, and it's going to be of type node pointer, and we're just going to call it nodes. So we can store any pointer to a node in this. So what do we want to do? Well, when we get a float expression, this is the point at which it's all been interpreted down to a single value, and float expression is that value. So what we can do is we can go simply like this. We can say nodes dot push back new, and we need to use a literal double and we'll pass it in $1. Okay. And we can do the same thing here, but with integer. So I'll just take this out. I'll copy all this. Place it here. Double T. No, it's going to be double E. And this will be int. Okay. I believe that should compile, but we won't see anything output now. Something doesn't line up. Oh, I didn't include my AST for one thing. So we'll come down here and we'll say include AST.h and see if that fixes it. Nope. What did I do wrong? Nodes dot pushback. Literal. Okay. Literal. What did I do wrong here? Literal. It's literal. Okay. Easy to make typos. Okay, that built, and we can run it. We'll do the same thing here. We'll go back to this. I'll expand this up a little bit. Devil compiler design tutorial. CD build. We'll run it. So we've got our loop again. 2 plus 3. And it does nothing. It doesn't print out the answer anymore. So how are we going to print out the answer? Well, I don't want to print out the answer in the compiler processing it. I want to print. Oh, I shouldn't have closed that. Let me get back in here. Devil compiler design tutorial. CD build. And make it bigger. Make it big. There we go. We'll minimize it. I really want to print out answers or whatever is happening here in my main function. And that's the final piece of this, the print part. Putting out something that's useful to the user after you eval the command, which would happen right here. We would print the result. To do that, we need to get a result. Well, parser.y, or excuse me, eval down here doesn't really return anything. It returns a 0 or a 1 or a 2 depending on whether this succeeded or failed. We need to return something else. In fact, what we need to return is our vector of nodes that have been generated by that command line. And the reason it's a vector of nodes is each node could be in itself a tree, and we'll get to that. And there could be several of those. We'll have some ability to put multiple commands on a line, and I'll show you how we will do that eventually. So we'll compile all of them, produce different trees for them. So how are we going to get a result back from this? Well, this finishes parsing, and this is right here where we want to figure out the result that we want to return. So over here in our abstract syntax tree, up here at the top, I'm going to create another class, and I'm going to just call this result. And actually, no, I want to put it below node. And I'm going to have a protected area here, and I'm going to also include vector, and I'm going to include I'll wait on that. All right. So this is going to contain a standard vector of node pointer, and it's just going to be underscore nodes, except yes, and this is going to be our result thing. And then what we will do is we'll have public, and this does not need a constructor. We're going to say in here we're going to have a void add node pointer node, and we will go underscore nodes dot pushback node. And then we're going to have standard vector node pointer get nodes, and we will return nodes. All right. So this is going to be our result. So what we're going to do up here in our parser is we want to return a result from this. And to do that, actually, we're going to add one more function here. Let's go standard. Let's go. I didn't want that. Get nodes, add node. What I want here. Okay, void add nodes. This will be a standard vector pointer to node nodes. And what we'll do is we'll just go for auto node colon nodes add node node. So I'll just punch them all in there. So what we can do is come down here and go result. We can do result dot add nodes and this is our nodes up here. And then instead of returning RV, oh, that's right. Let's go back to here. We need a constructor. We'll do int result. We'll go result int result int underscore result underscore result. There's our, and we'll do down here, we'll go int get result return underscore result. So now over in parse.y we can do result RV add nodes and return result. Okay, now over in main we have to change this to result, and we have to include our AST found. And here we need to get, this needs to be result equals eval, and we should be good. Let's compile. Whoa, what do you know? I did all that coding and no errors. That was awesome. Okay. So now we've got a result coming back, so what can we do with it? Well, after we get this back from here, instead of a bool, we actually want to return that result again right here. And so we will return, what we'll do is go return eval line. Okay. And so instead of running equals this, we'll go result equals. Now we've got that. We can say that running equals result dot get result equals 1. I think we will only return that result 1 when we get an error. Yeah, we'll do that when we get an error, I think. So let's see what happens. Okay, it liked it. Let's run it and see if anything weird happens. Three plus 2, and we quit. Okay. I think I had that logic backwards is all. 3 plus 2. Yeah, 4 plus 5. Okay. So we're getting a result back. Now what we want to do though is go something like this. We want to go for auto. Oh, we really don't have an abstract way of doing this, do we? Let's go back to our AST. Let me double check the time real quick. Okay. Our node class does need that toString. So we want to be public standard string toString equals 0, and in this we need to implement that toString. So we can go standard string standard string toString. It's got to be virtual. This one up here has to be virtual. toString. And then what we can do is do this. I know what we can do, exactly what we can do. Okay. We're going to include stream. And in our toString on this, we'll go standard string stream SS. We'll go SS from underscore value. Oh, wait a minute. I'm putting this in the result. That's the wrong one. We want it in this. There we go. We want it in our literal SS from value, and we're going to go return SS dot, is it toString? Let me see if that's what it is. No. It's just str. That's right. Yes. So now that we have an abstract toString, what we can do here is do this. We can go for auto node in result dot get nodes. Now these are going to be pointers, so what we can do is go standard cout from node pointer toString from end standard endl. Now, one thing I want to do over here in the parser is every time I return this result. We did the add nodes. They're all in there. I want to go nodes dot, is it clear? Yes. Oh, let's not do it there. Let's run it here where it's big. So we go 3 plus 2, and it's 5. We go 4 plus 7, and it's 11. We go 3.2 times 6, and it's 19.2. And so what's happening? Instead of, so it's doing all the math. The compiler's doing all the math, but it's taking that final value and it's putting it into a node for that specific kind of node, and then abstractly we're able to go through each of the nodes and tell it to give us that string. Now we can do other things. We can have commands, we can have it execute stuff or do things, pass a context into it so it can act upon things, or just extract information that we need from it and execute those commands in a different way. There's a lot of different ways of doing it. Or we can emit some sort of code appropriate to it. So that is how we can start building an abstract syntax tree. So let's start thinking about what kind of commands we can create now. So we've got this, oh, you know what, there's one other test I wanted to do, because I think if we get a syntax error, if we type garbage in, we get a parse error, but we don't exit the code. That's good. We'll make these errors better in the future. We'll actually print out some useful information about what you did wrong on a command once we start growing the system up. But for now, parse error will be fine. Let's real quick go over here to lexer.l. Now, I've got this ident here. And idents are something that we want to look at kind of last in our group of things here, or near last. We want to look at other things first, because keywords, if it can't find, so we're going to start creating a keyword now. And in fact, let's create it up here. Let's call it quit, and the keyword will simply be quit. That's it, exactly what it is, QUIT. So if it's not a keyword such as quit, then it might be an identifier. So we check the identifier last. If you check the identifier before your keywords, what'll happen is that your keywords won't show up. They'll all be viewed as identifiers. So quit's an easy one. We're simply going to return t quit, which I haven't created yet, but I will. So we go over to parser.y. It's a just straight up token. We can stick it right here, t underscore quit. And a line. Oh, and this error token in here is why we don't die when we get a parse error. And that's where we will also put some stuff to make better error messages. But right now I'm going to say that a line can also be a command. And we'll create command right here. And right now it can just be t quit. That's the only command that we have. Semicolon. But what is t quit going to do? It's going to call YY abort. And what that'll do is return a non-zero from our compiler, which will cause us to quit. Let's do a make. And let's go up to here and let's see if that works. Let's run it. And we'll just start off by typing quit. And we quit. So what we can do in our main function here is say, if you quit, you're going to end up outside the while loop. Shoot. Let's get rid of that. Down here we can go standard cout from goodbye build it here. And so now if we type a command quit, and that's how simple it is to make a command. We'll make other commands as we go along, and we'll make stuff that can store stuff in variables and save information and update stuff and create things and all kinds of stuff. And we will also end up making more than one compiler, all running in the same application. I envision that we'll have a compiler that will set up rooms. There'll be some text description of all the rooms we want. It'll compile that and build the room structures when it reads it, sort of like a configuration file, but it'll have structure to it. And then there will probably be a language that you can use to create other commands and stuff that runs inside the game. And so what we'll do is we'll create another dungeon crawl game. We'll call it Dungeon Crawl 2. It'll be much more sophisticated, and we'll have a sophisticated language that we can do both on the command line, and we can write scripts for it and load them in, and the scripts will run. We can set up actions and events and all kinds of stuff. So that's kind of where we're heading with this. I'm starting to design a couple of those languages that we're going to use and how we're going to use them, and we'll start building them into this as we move along. So I think that's about it for this video. I'll try to keep these reasonably length. Yeah, it's 31 minutes in, so thanks. I hope you enjoyed the video. If you liked it, hit that like button. If you really liked it, hit that subscribe button, and I will see you in the next video. Thanks for watching.